The invitation to deliver a talk at the NanoScientific Symposium this year. My name is Kwabena Bediako, and it's a real pleasure and privilege for me to tell you about some of the work we've been doing in my group. And of course, none of this work would be possible without an exceptional group of graduate students, postdocs, and undergraduate students as well. And so I have this team to thank for everything I'm going to show you today. And I'll only really be talking about a small fraction of the work in our group. And specifically what my group does is try to understand and control energy flow. A lot of the time it's across solid liquid interfaces and also through solids. And this is because ultimately some of these processes are central to energy conversion technologies, and we'd like to try to understand the fundamental science that we need to improve the efficiency of these systems. And today I'll be talking specifically about our work trying to tailor and measure charge transfer across a solid liquid interface. And that's because one of the questions that drives us is how can we produce fuels and chemicals sustainably? And so both the regimes I showed you before, where the solid liquid or solid charge transport, are very, very relevant to some of the most pressing challenges that we face in terms of energy sustainability. And so harvesting solar energy, for example, relies on our knowledge of how to convert energy from photons into separated charge carriers that move within a solid and can be used to do useful work. And sometimes that might involve converting that electric energy into chemical energy at the interface of catalyst liquids and so on. Okay, and so our goal in this context is to ask, how can we deterministically control the physics of solids and surfaces and use that to try to manipulate interfacial electrochemistry and ultimately to drive electrochemical processes more efficient. And our work specifically is on the very fundamental side of this problem, trying to find new ways of controlling materials properties. So the main takeaways from my talk are as follows. I'll introduce you to how flat electronic bands in Moiré superlattices of graphene can be used as topological defects that then enhance interfacial electrochemistry and can be used to tune interfacial electrochemistry. And I'll show you how the twist angle modulates the interfacial electrode kinetics. No doubt you would have heard in the talk before me from Professor Hone about all the really interesting physics that emerges when you can twist these types of atomic layers. And in fact, I'm sure you have heard some really exciting results about twisting and measuring in situ, which is really cool. And so we are looking on the sort of chemical side of this to say what new chemistries can we learn. And I'll show you how the spontaneous relaxation of the Moiré lattice, how that influences the electrochemical kinetics, particularly at small twist angles. Okay, so to get everybody on the same page, in electrochemical studies, what we're interested in is using an electric potential across a solid electrolyte interface. Sometimes the electrolyte is a liquid, sometimes it's a solid, to drive an interfacial electron transfer reaction. And a really nice phenomenological model that is typically used to explain what we observe experimentally is called the Butler-Volmer model. And this basically describes a situation where the rate constant for the reaction is related to the free energy of activation of that reaction. And so as you apply a large overpotential, a potential in excess of the thermodynamic potential, this increase in overpotential is serving to decrease this delta G double dagger. And so then it is assumed that this delta G double dagger is changed as a constant fraction of the applied overpotential in the Butler-Volmer reaction through this transfer coefficient. And this model is really useful. It works in many cases, but it's quite limited in explaining certain asymmetries in some electrochemical responses or TAFL responses. And it also is actually very limited in describing cases where the electrode electronic structure, the density of states, is not necessarily constant as a function of energy. And so instead, we need to think a little bit differently, using Gerischer's formalism or the Marcus-Hutchitzi model, which describes the rate of electron transfer in terms of the density of states of the electrode, the electronic density of states of the electrode, and the probability distribution function of the solution redox couple. So you could think of this as the homo-lumo levels of the molecule in solution. And this approach is used a lot in semiconductor electrochemistry, where the electronic structure of the electrode is very, very important. It's not used so much in more conventional measurements, say chemical engineering, aside from semiconductor electrochemistry. And this is because basically the Butler-Volmer model is so much easier to implement. And so while this model has existed for a while and is known to be very important, we don't use it a lot. But it turns out to be critical when you're trying to make sense of the behavior of certain systems. And okay, and so the point is that this model teaches us that the density of states of the electrode is very important to the overall rate. And as I was saying, more recent studies suggest that we need to go beyond the Butler-Volmer model. And these types of considerations of density of states may be warranted even for transition metal surfaces where you have the bands from d orbitals that are highly non-dispersive, where they play a key role in the facial charge transfer. Okay, so this model tells us that the rate constant for our reaction is some function of the density of states of the electrode and the probability distribution function of the molecules in solution. And as described in that equation, that applies simply to an outer sphere charge transfer reaction where there's no bond formation process. But even for catalysis, the electronic structure of the electrode is very, very important and can actually be used to explain trends in hydrogen evolution activity across the periodic table. Okay, and I won't go much more into that other than just to drive home the main point of this whole introduction, which is that manipulating the band structure of solids is very, very important to understanding and more efficiently driving interfacial chemistry. And there are a number of examples where we basically managed to facilitate interfacial charge transfer using this general idea. One is in the exploitation of defects, right? So atomic vacancies, for example, in this case, molybdenum disulfide, they create sort of mid-gap states, defect states in the material that show up as localized electronic states if you were to measure the density of states indirectly using, say, scanning tunneling spectroscopy. And these states are implicated in the hydrogen evolution behavior and activity of the basal plane of MOS2. So that usually the more defects you have, the more active your material is. Likewise, steps and edges of materials are commonly implicated as the active sites, right, in interfacial catalysis. And then another example is in the case of dislocations and grain boundaries that actually have very interesting selectivity implications. So the point of all this is to say that defects, which we know can have very, very different local electronic structure from the pristine or bulk, tend to be reactive hotspots in interfacial charge transfer reactions because they tend to have these localized electronic states, but they're very, very difficult to control at an atomic level. And so my group uses two-dimensional materials, and ultimately our goal is to say, can we develop very, very tunable models for interfacial charge transfer that can teach us something new. And so many of us here, I think, would appreciate that some really interesting physics emerges in 2D solids for a variety of reasons. And this came to the fore in the case of graphene, some almost 20 years ago now, where some really distinctive properties of electrons in graphene were observed and measured for the first time. And since then, the family of 2D materials has expanded and to materials that have a wide array of structures, compositions, and electronic properties. And what's of course really nice about these, as you heard before, is the fact that you can assemble them into sort of stacks, atomic field Legos with each other. And as you heard in the previous talk, these layers can slide over each other and form these Moiré superlattices, where the twist angle controls the length scale of this Moiré superlattice and basically the crystallographic registry between the layers. And so in this Moiré superlattice, you have different types of stacking. So what is changing as you go from one region of Moiré superlattice to another is just how these lattices are on top of each other. And since about 2011, it was known that as you change the twist angle between graphene layers, you expect it to have really, really flat bands emerge in the band structure. And it wasn't until about 2018 or so that the full potential of these flat bands, you could say, perhaps was realized in the discovery of correlated electronic phases in twisted bilayer graphene. And so there's been a surge of interest in these Moiré-based systems, particularly for the exciting and exotic low temperature physics that they display. And this is not just the case for graphene, but across the family of atomically thin layers, these Moiré materials have been shown to exhibit a wide array of twist tunable electronic properties. Right? Okay, so our question was to ask whether these flat bands, can we use them to manipulate and modulate interfacial chemistry? And so we looked at the density of states enhancements that we expected for magic angle bilayer graphene, and which had been measured as a function of twist angle using scanning tunneling spectroscopy. And we thought back to the role of sulfur vacancies in creating these localized electronic states, in that case within the band gap of pristine MOS2, and started wondering whether these localized electronic states would also serve as reactive hotspots for interfacial chemistry. And if so, then the twist angle dependent density of states should be itself a descriptor of the rate constant. And so again, looking back to sort of this example here and thinking about how these Moiré derived flat bands might serve as reactive hotspots for chemistry. And so we went ahead and did this experiment. We use our, since this is a PARC conference symposium, I think I should at least mention that. We use our PARC NX10 system, which allows us to do scanning electrochemical cell microscopy experiments. So we take a nanopipette, we fill it with electrolyte. The electrolyte protrudes a little bit from the base of that nanopipette. We can touch down onto our sample, and we can do electrochemistry within that little meniscus using this system. And this is really nice because it allows us, in principle, to do spatially resolved electrochemistry. Typically, our pipette size is about 100 to 300 nanometers. And so the length scale that we're probing in these experiments is not sort of sub-Moiré length scale. It's sort of an ensemble over the Moiré. But nevertheless, because of the size of the samples that we make, this is really, really convenient because these samples that we make are typically on the few micron scale. So here is an optical micrograph of the device where we have a twisted bilayer graphene sitting atop hexagonal boron nitride, and then we have a contact here. We use, we get STM, these are just ambient STMs, also using the NX10 system. And so we can visualize the Moiré superlattice by mapping using STM, and then that confirms. But then we go ahead and do our scanning electrochemical cell microscopy measurements. And I'll just walk you through one example. So here we're probing the ruthenium 3 2 couple in this ruthenium hexamine. redox reaction, if we were just to take a monolayer of graphene and sweep its potential, what we would see, or what we do see, is this S-shaped curve, which is as we expect for this nanoscale sort of electrochemical experiment, where the curve is offset from the equilibrium potential of our ruthenium 3,2 couple, simply because the kinetics of the reaction are relatively slow. And we can understand this as arising from the fact that graphene has a low density of states. And so according to our Marcus-Hartshitzi model, we would expect that low density of states to manifest as a low rate constant, right? And so the kinetics are not as facile. And so we have to pay a price in overpotential to drive the reaction. As we go to bilayer graphene, we have more density of states to work with, so that increases. And if you were to go to a bulk graphite or piece of platinum or gold, you see that now your voltammogram is straddling this E naught, which means that it's reversible, a reversible reaction. So what happens then if we take two layers of graphene, but instead of having them Bernal stacked, we twist them so that they're close to about 1.2 degrees? Well, now you find that they behave for all intents and purposes like the bulk graphite. And so electrochemically, they're behaving as though they have a lot more, it's behaving reversibly. And so that sort of was our first hint that, we might have something interesting here, that our hypothesis that twisting can control the rates might actually lead to something. So we can go ahead and make samples at different twist angles. Again, here are the STM images, just showing the variation in the Moiré superlattice periodicity. We can measure the electrochemistry of these samples, and we can plot then the rate constant on this semi-logarithmic plot as a function of the twist angle, and we see that there's a very, very strong modulation in the electrochemical rate constant as a function of twist. So this was for the ruthenium 3,2 couple. We can sort of test our hypothesis that that this has something to do with the flattened bands by measuring the same electrode kinetics at another redox couple that we know is very, very misaligned energetically with the neutrality point, or for that matter, the flat bands of our twisted bilayer graphene. And so this cobalt for nanotechnology 3,2 couple shows a much more quenched effect on of the twist angle, which is in line with the fact that by the time we've applied enough potential to drive the cobalt 3,2 couple, we're well away from the flat bands in our Fermi level. And in fact, we see if you look at this and you might say, oh, there's a little bit of a maximum, above 3 or 4 degrees, and that is just as we expect, pretty much for where the Van Hove singularities would show up for a twisted bilayer graphene. So there is a very small enhancement at about 3 or 4 degrees, because that's where at that angle you have some small enhancement of the density of states of your graphene, which is much diminished from what you get at the magic angle, but nevertheless. So all of these taken together was quite encouraging, that we can understand the origin of this effect, at least to a first order approximation. So to go a little bit deeper, we have to recognize that what these flat bands mean. Flat bands in reciprocal space means localization of the electron wave function in real space, and this has been known for a while, but just to sort of show you some of the calculations here as well. If we look at a twisted bilayer graphene of 1.1 degrees, you see that the density of states enhancements that are, that you could measure for the whole system are mostly localized, or overwhelmingly localized, on these AA sites of the graphene, and much less so on the rest of the graphene structure. And whereas at 3 degrees, you have a more smearing out of the electron wave function, and very little discrimination between the different stacking types. And so a number of things come out of this. One is that at large angles, you have this smearing out of the electron wave function, and you also have much less localization. so no flat bands at larger angles. And so we can understand this drop off in the rate constant for our ruthenium-32 couple is simply arising because at large angles we're eliminating the flat bands from our electrodes. But what is going on at these smaller angles, right, where we expect that you should still have you should still have flat bands, at least for these, room temperature experiments. The bands in this regime should always be flat enough that we'd expect to see some effect. So what's going on there? And to understand that, we need to think a little bit about the actual structure of twisted bilayer graphene. So when I show you this picture here, it's of course a cartoon that assumes that the lattice is rigid, but this is not the case. It's been known for a while that the graphene lattice should relax to adopt a lower energy structure where the relaxation mechanics are proposed to involve localized rotations of these AA regions that twist further to try to shrink their size, and these AB and BA regions that untwist. And so what my group tried to do was to go in and actually find a way of measuring these local rotations and the resulting strain that we expected to observe more directly. And so we went ahead and did that using a technique known as 4-dimensional scanning transmission electron microscopy. And so what we're doing in this technique is we are rastering an electron beam over our sample. And at each probe position, we're acquiring a diffraction pattern so that our 4D STEM data set is just this compilation of diffraction patterns acquired at each point in real space. And we can go ahead then, and what we make use of in this technique is the overlap between the Bragg disks from one graphene layer and another. And we can map that onto the local stacking orientation of the sample. And specifically, we can map that onto the displacement vector between one layer and another. And so we end up with maps like this, where at each pixel, the color assigned to that pixel gives you information about the X and the Y component of the displacement vector of the sample. And so it gives you a visualization, a quantitative visualization of the Moiré superlattice, so that at each point the vector, the direction and the magnitude of the displacement vector between one carbon atom and the next. And what you'd expect if there was no relaxation at all in the system will be a gradual transition between, say, the white to the orange, the white to the red, and to the purple as you went around the sample. But instead, we see these very, very sharp sort of transitions, almost like domain walls, which is indicative of some deformation to the rigid Moiré lattice. But we can go a step further than that. Apart from just qualitatively visualizing this, because we have a displacement vector field, we can take the gradient of that displacement vector field and extract the 2D strain tensor field at each point in the sample. And from that 2D strain tensor, we can determine the local rotations, the so-called fixed body rotations of our system. And if we then take into account the Moiré twist itself, we can get out the relaxation rotations, the rotations that are present in addition to the Moiré twist. Therefore, the ones that are responsible for the relaxation process. And so sure enough, we can measure these and see that at AA sites, indeed, we have a further twisting, positive twisting of the Moiré superlattice. And then at these AB and BA sites, there's an untwisting. And so this was, our measurement and our first sort of direct experimental measurement of the relaxation process that had been predicted from theory and that had been visualized and sort of hinted at indirectly from some other microscopy measurements. But what we were able to do, because we can quantify this relaxation, we can plot the local AA rotation, in other words, if you were just to put blinders on and you didn't know about what the Moiré twist was, and you just measured the local twist between one carbon atom and the next, and between the two layers, we can measure that as a function of what the global Moiré twist is, and that's this blue curve here. And what you find is that because of this relaxation process below about, I would say 1.6 or 2 degrees, you find that the twist, the total AA rotation is more or less constant, pinning to a value of about 1.2 degrees or so. Whereas at larger angles, it would follow this this gray line, and be the total rotation would more closely match the Moiré rotation. The importance of this is that when we do these experiments, in our SECCM experiments, our electrochemical experiments, and we're measuring these kinetics as a function of twist, remember our pipette is maybe 100 nanometers to 300 nanometers in size. And so what we're doing is we're doing an ensemble measurement over the entire, many Moiré superlattice sites. And so that's what this measurement is. What we can do, since from our 4D STEM measurements, we also know the area fraction of AA and AB and so on, we can take this ensemble measurement and pull out the rate constants associated with the AA sites alone. And what we find is that they follow this trend where their activity, their rate constant increases as you decrease the total Moiré twist angle, and then below about 1.5 or so or 2 degrees, it reaches a plateau. And so already you might be seeing how these two things are related, because knowing that the AA sites plateau, you can in their activity, you can relate this back and understand this from the perspective of these local rotations that we've measured. We know that the local rotations are distinct from that initially imposed Moiré angle, and that the AA regions locally plateau at about 1.2 degrees. We measured that. And so the reason that the AA sites also attain a plateau in their local electrochemical activity is because their local rotations are all constant. In other words, their local and electronic structure is, for all intents and purposes, at room temperature, is the same, irrespective of the Moiré angle. And all you're changing as you go from this point to this to that, as you change the Moiré angle and decrease it below about 1.5 or 1.6 degrees, is you're simply spacing out these reactive hotspots from each other. As you decrease the angle, you're spacing these out. And so in that sense, these AA sites are a type of defect, right? These AA sites are indeed a topological defect that is introducing a large localized density of states, and we are able to modulate the defect density very precisely, and we have a very, very controllable defect, right, which is controlled by the Moiré angle. So we're very, very excited about this platform now for studying interfacial reactivity, where we have the ability to create these flat electronic bands that so that we can probe the effect of these types of electronic structures on electrochemistry, and understand real systems, even say transition metal surfaces that have very, very narrow d orbital based bands, and for which theory has not yet caught up to the real experimental type of system, because there's a knowledge gap in having these controllable materials where you can systematically tune the electronic structure and measure the electrochemical behavior. So we're very excited about this platform. We're extending it to multi-layers now, which gives us more possibilities for modulating the electrochemical behavior, many orders of magnitude more than what we've seen in twisted bilayer graphene. We think that there are significant implications then for catalysis, where the binding strength of the intermediate can be tuned by the angle, and then even using electrostatic gates, for example, to tailor this further. Okay, so again, here are the main takeaways. I hope to have shown you how these Moiré superlattice-based flat bands can be used to modulate interfacial chemistry. So the twist angle itself then becomes a descriptor of the interfacial kinetics, and how lattice relaxation that we've measured by 4D STEM helps us to understand the twist angle dependence. I'd like to end there by acknowledging my colleagues, my coworkers in my group, collaborators, who, without whom this work would not have been possible, particularly the Viswanathan group at CMU that basically did all the theory work on the electrochemistry project and have been working with us on this. So with that, I thank you for your attention. I'm happy to answer questions by email. If somebody, if you'd like to reach out, I'm happy to answer questions about this presentation. Again, I apologize that I could not be with you live to answer your questions. Thank you, and I hope you have an enjoyable rest of the symposium.